Hello, everyone. Welcome to pre-lecture 27. Hope you had a good Easter. I'm ready to talk about some oxidation reduction reactions. So just to start with defining some terms, anytime we have a chemical reaction that involves the transfer of electrons between our reactants to make products, we call that a reduction oxidation or a redox reaction. One truism with this is that you cannot have reduction without oxidation, and thus you can't have oxidation without reduction. So you need both in order to have this reaction occur. Reminder from Gen Chem 1 that when something is reduced or when reduction occurs, that means it is gaining electrons, whereas when something is oxidized or an oxidation occurs, that means a loss of electrons. If it's helpful, you can think of the acronym oil rig. So oxidation is loss and rig is reduction is gain, to remember which way your electrons are moving. Something that may be a little difficult to keep straight, part of why we're doing it in the pre-lecture video, is a reminder that compounds that gain electrons as reactants are called oxidizing reagents, in that because they are reduced, they do the oxidizing, whereas compounds that lose electrons are called reducing reagents. Okay. These are extremely important reactions for things like batteries, also many, many biological processes. That's why we dedicate a whole chapter to it in Gen Chem. Okay. So oftentimes we track a redox reaction by assigning oxidation states to the elements that are within these compounds. We can do this following certain rules. And so just fair warning, I'm going to go through these pretty quick. But these are things you will need to know in order to be successful in this chapter. So if that means memorizing these, then I would memorize them. In an ideal world, though, you would be able to understand the process here and thus not need to memorize. So anything that is a free element, so it can be a single atom. It can also be something like O2, dioxygen, is a single element, meaning that the oxidation state for each atom is going to be 0. We then have monoatomic ions. So those are ions that have an oxidation state equal to their charge. And so the sum of all oxidation states of all the atoms in a compound is 0 if overall the compound is neutral. And the sum of oxidation states for polyatomic ions is equal to the charge on the ion. So for example, something like sulfate, SO42-, means that the oxidation states of our 4 oxygens and our sulfur have to all add up to a net of -2. And we'll talk about some different examples in this video and in class. Okay. Group 1 and group 2 metals, so these are the 2 columns on the far left side of the periodic table, have oxidation numbers that correspond to their row. So something like lithium has a charge of +1 always, or almost always, and then something like calcium or magnesium has a charge of 2+. Some elements always have the same charge, and the priority that we would assign these in is that fluorine is always going to have a charge of -1, hydrogen has a charge of +1, oxygen has a charge of 2-, unless it is a peroxide, in which case it will be -1. Then the group 17, so that's starting with fluorine and then chlorine, bromine, iodine, have a -1 charge. Group 16, which is oxygen, sulfur, selenium, have a charge of 2-, and group 15, which is nitrogen, phosphorus, arsenic, have a charge of 3-. Okay. All other element oxidation states can be calculated on whatever is left over in order to fulfill the rules of equaling the sum of oxidation states for the compound. Okay. Right, we have another set of rules, and so we can also balance redox reactions then in a systematic manner. And so the rules here, first thing is assign oxidation numbers, which is what I went over on the previous slide. You want to determine the oxidized element and the reduced element. We want to then write the oxidation half reaction and a reduction half reaction, including the electrons that are transferred. Then you want to balance all of the elements that are oxidized and reduced, and then balance the oxidation states by adding electrons. Next step is to balance the charge of the half reaction. And so these charges need to be balanced on both sides. And if we are balancing things in acidic solutions, we add H+. If we're balancing things in basic solutions, we add OH-. Then we balance the oxygen and hydrogen atoms by adding water. So all likelihood, we'll do that to one side. Finally, or penultimately, I guess I should say, we balance the number of electrons between half reactions by multiplying each reaction by some sort of integer to get our electrons balanced. And we add our half reactions together and add phase labels. Finally, check that the number of atoms and charges are the same on both sides, and all electrons should cancel out, and potentially some atoms may cancel out as well. Okay. So in our in-class worksheet for chapter 19, or chapter 17 rather, sorry, we can go through an example here. So this is 1A, balancing this redox reaction in acidic media. So if I start with the steps of defining oxidation states here, following our rules, looking at our first molecule, BrO3-, we know that oxygen should always be 2-, and we have 3 of them. For a total charge of 6-, and our overall molecule charge is -1, so we know that the plus on bromine must be 5+. Okay, that's BrO3-. We look at our other reactant, our N2H4. We know that H+ should always be +1, and we have 4 of them, so that's a total charge of +4. Then nitrogen, we'll have to balance that. And so our 2 nitrogens have to have an overall charge of 4- because our molecule is neutral, right? We don't have any charge up here. And because we have 2 nitrogens, each of those nitrogens has a charge of 2-. Okay. We look at our product side, bromine, or bromide, I should say, is just that atom. We look at its charge to find its oxidation state. Oxidation state would be -1. Then our other product, N2, it is a pure element. So even though we have 2 atoms, it is just a single element. And so its oxidation state would be 0 there. Okay. So if we want to balance this reaction in acidic media, we split our reaction up into the reduction and the oxidation. So we need to figure out what is oxidized and what is reduced. I'm going to change colors here. If we look at bromine on this side, has a charge of +5. Bromine on this side has a charge of -1. Because its charge is getting more negative, that means it is going to reduce, right? So our reduction half reaction would be start off by saying it's BrO3- turning into Br-. Okay, and I'm going to pop there, switch colors, so we can talk about our other reactant that is oxidized. And so nitrogen goes from being 2- on this side to being 0, so it gets more positive, which means our oxidation half reaction involves nitrogen going from N2H4 to N2. Okay, and so if we follow the steps, and I'm going to go back to our reduction half reaction to start here, we want to balance all of our elements that are not oxygen or hydrogen, which in this case would mean just bromine, and it's already balanced, so that's great. Then we want to balance the number of electrons. And so if we go from an oxidation state of +5 on the reactant side to -1 on our product side, we would have to add 6 electrons in order for that to happen. You always want to add electrons to the more positive side. And so we add 6 electrons. and that evens out our number of electrons. Now we're trying to balance this in acidic media. So we've balanced our electrons. Now we want to balance our charge. We look at our charges. We have 6 negative charges here, 1 negative charge here. So total minus charge of -7 on our reactant side, total charge of -1 on our product side. And if we're balancing this in acidic media, we'll be adding H plus. And so in order to balance things out, we would add 6H plus, because that would get the charge on our reactant side to even out to be -1, whereas the charge on our product side is also -1 now. Okay. So we've balanced that. And finally, we need to balance our hydrogens and our oxygens with water. So we have 6 hydrogens and 3 oxygens on our reactant side. We have 0 on our product side. So if we add those in, I tend to balance oxygens. So I know we need 3 H2Os, balance just our oxygens, get 3 oxygens on each side. And that should simultaneously balance our hydrogens. And so that gives us 6 hydrogens on our product side, 6 hydrogens on our reactant side. And we are sitting pretty. So we have a balanced electrochemical reaction for our reduction reaction. If we think about our oxidation half reaction, we're going from 2 times 2 minus, 4 minus overall, to 0. And so we would need to add electrons, and we would need to add 4 electrons to the side because we're going from 4 minus to 0. Again, you always add your electrons to the more positive side, or the more positive oxidation number side. So 0 is more positive. That's why we put 4 electrons on that side. We would need to balance our charge next. So we have a charge of 0 on our reactant side. We have a charge of 4 minus on our product side. So we would add 4 protons because we're balancing it in acid again. So we add our 4 protons, and then we balance our oxygens, our hydrogens. In this case, they're actually already balanced. So we don't need to add any waters. And that would be our balanced reaction for oxidation. Okay, last steps are we need to add things back together, and we need an equal number of electrons to do that. And so we have 6 electrons in this reaction, 4 electrons in this reaction. We multiply this reduction reaction by 2 and this oxidation reaction by 3. That'll give us 12 electrons total. And so if we are going to combine things and rewrite, we end up with 12H plus 12 electrons plus 2BrO3 minus plus 3N2H4 is our reactants, turns into 2Br minus plus 3N2 plus 12 electrons plus 6 waters plus 12H plus. Then we can look at our products and reactants and cancel out like terms. So our electrons should always cancel out. So we'll cancel those out. And then in this case, our protons actually cancel out. So we have 12 protons on our product side, 12 protons on our reactant side. Those would cancel out. So our final answer would end up being 2BrO3 minus. We can add our states back in if we would like. 3N2H4 gas goes to 2Br minus plus 3N2 gas plus 6H2O as a liquid. Okay, that would be our final answer. So hopefully that made sense. We're going to continue practicing these in class. And so if you have any questions, please let me know. Otherwise, we'll keep practicing in class. And I hope you have a good rest of your day. Take care.